All right, good afternoon. So I'm John Honstein, the chair of the SIAM activity group on algebraic geometry, and welcome to our prize ceremony. So we'll start with poster prizes, and Heather Harrington will give out our poster prizes.
Thanks, John. I'm sorry, you have to bear with me. I've been talking a lot. I lost my voice a bit. So I'm Heather Harrington, and I'm part, I guess, chair of the poster committee, which was made up of Baron Sternfels, Mike Stillman, Rebecca Thomas, trying to look who else, and John Howenstein, of course. Sorry, I was like, where's the other person that? And so we were really impressed with the quality. We had a little over 30 posters this year. Really, really impressed with the quality, and it was a difficult decision. We looked at the presentation, the actual content, so theory and applications, and also how all of the presenters actually presented their poster. And so it was such a difficult decision that we have 2 best poster prizes and a runner-up. So the 2 that are sharing the poster prize will get 1 free year of SIAM membership, one of the cool shirts that all the volunteers are walking around in, and they get a free activity group membership as well. So the 2 best posters were really a tie. Yeah, exactly, drum roll. So we had Nita Obataki. And if you're here, please come down. And it's Nita here. And the other winner was Jane Coons. So really well done. Okay, so just a word about each of the posters. So Nita's poster was titled "A Constructive Algorithm for a Positive Solution to a System of Polynomial Inequalities." And in her poster, what was really impressive is what one could not compute. Their sign conditions that one would want to calculate in the systems in the specific example in biology was so large that you couldn't do this. And she came up with a new method using Newton polytopes. So it was really, really impressive. And specifically that you could see that instead of the multi-stationarity, which is a question that most people are looking at biological systems, this was looking at oscillations, so it's even more difficult. So that was really impressive. And then are either Nita or Jane here? I'm here. Okay, great. And so Jane, yeah. So I have a certificate for you, and a T-shirt.
Oh my gosh, thank you.
Congratulations. So here we go.
Thank you so much.
Congratulations. Right, so Jane, I don't have the exact title in my head. So it was, where are we? Oh, I gave it to you. You know that, I was like, where is it? But basically what Jane proved a conjecture that Caroline Euler made some years ago on the maximum likelihood degree, and actually proved this. And so it's quite a big result, and we were very impressed with your poster. So congratulations both. Okay, and then the runner-up. It was really a difficult decision. So we have a runner-up, and it's Gleb Pogudin. And his work, he actually fills, is Gleb here? Oh, right here in front, great. So Gleb's poster was parameter identifiability for ODE models via an input-output representation. And what is really impressive is Gleb has filled a gap effectively in the identifiability theory. So that was really impressive. And so you get...
May I say that I have 2 collaborators?
Oh, of course, go ahead.
I just want to mention that it's not my own work, it's my 2 collaborators, Alexei Shinnikov and Peter Thompson from CUNY. There are 3 of us, okay?
But I'd like to point out that we also judged how the people presented the posters. So you were the one presenting it. So congratulations. Okay, great. So I'm going to leave Nita's here and hand back over to John.
So thanks, Heather. So just outline for the rest, there'll be a quick introduction to what is the Early Career Prize. We'll have the Early Career Prize lecture, and then there'll be a very short advertisement at the end after all of the questions regarding the lecture. Okay, so let me tell you very quickly about the Early Career Prize. So it was established in 2016 and given out for the first time at AG 17 in Atlanta. And the winner in 2017 was Pierre Larez. The Career Prize is given for a distinguished contribution in the 3 previous calendar years. So those are 2016 through 2018. And you have to have your work published no more than 3 years after your PhD. I want to thank the selection committee, Teresa Crick as the chair, Elizabeth Ullman, Henry Cohn, Mikhail Yuswig, and Agnes Santo for serving on the committee. We had many wonderful submissions, and I hear it was a difficult decision. So thank you for all your submissions as well. So the actual prize itself is this wonderful lecture. We have a beautiful certificate up here, and then we have a 3D print of a Degree 6 surface that Danielle Brake and myself designed and have donated to the activity group. This is number 2 of 5 in our original set of prints, so we're making our way through the original ones. I asked the students in the front, your students here, how to pronounce that in proper German, and I have completely failed. So I will call it a seahorse. And so this year's winner is Elina Robeva. Congratulations. And the citation for her award is she had highly innovative contributions to the analysis of tensors, especially for major advancements in the theory of orthogonally decomposable tensors, and that will be the topic of her talk today. She got her PhD in 2016, and that was the same year that her contribution was published in the SIAM Journal of Matrix Analysis and Applications. So we'll get set up here and go for your talk.
Thanks. Thank you so much. So, hi everyone. It's a tremendous honor for me to have received this prize. Oh, I don't know if this is working yet. Especially since I'm in the company of so many excellent young researchers in our community. And I want to begin the talk by thanking all of my collaborators and mentors throughout the past few years. This is definitely not a complete list of the people, but I really like to thank Ada, Madeline, Juliette, Taylor, Emil, JC, Robert, Kaye, Luke, Cheng, Anna, Jeff, Nock, and Luca. And I would also like to thank the people who I collaborated with, but have also been mentors to me throughout the years. So that's Jan, Matthias, Pablo, Ben, Philippe, and Caroline. It was really wonderful working closely with Caroline in the last 3 years during my postdoc. And finally, I'm eternally grateful to my advisor, Bernd Sturmfels. He's given me an amazing mentorship and both academic and personal support throughout the years. It's always been really fun to collaborate with him, and he's amazing at connecting people and making new collaborations happen very quickly, which is why there's so many people that I've worked with. And I want to thank him and Caroline for nominating me for the prize, and I want to thank the committee for selecting me. Okay, so the talk today will be about tensor decomposition, and it's very nice that Tammy already presented a lot of this yesterday, but I'm going to go over the basics again, perhaps a little quicker. So I will talk about the same type of tensor decomposition that she talked about, which is the CP decomposition, which is the canonical polyadic decomposition. And this is a generalization of matrix decomposition. So here we express the tensor as a sum of rank 1 terms, and I'm going to define this more precisely in a little bit. And it's actually exactly a generalization of matrix decomposition where you factor the matrix into 2 factors. And if you've never thought about this before in this way of sum of rank 1 terms, I invite you to. And so as we saw yesterday in Tammy's talk, there are many applications of this type of decomposition, especially in machine learning and statistics, also in signal processing for blind source separation, in chemometrics, neuroscience, sports. Basically, whenever you have multidimensional data, by doing the decomposition, you might extract information about how the data was formed. Okay? And so, again, what are tensors? Tensors are multi-way tables, and we're going to have 2 cases, ordinary and symmetric. So in the ordinary case, we have an n1 by n2 up to nd table of numbers. And the notation of this is t lies in r to the n1, tensor r to the n2, up through r to the nd. If you're working over r, or if you're working over another field, you can replace it there. And then the symmetric case, we have an n by n by n d times table. And here, in both cases, d is the order of the tensor. And it's symmetric if you take any entry and you permute the entries, so t I1, I2 up to id equals to t at any permutation of the indices. Okay, and the notation for the space of such tensors is sd of Rn. Okay, and so what is tensor decomposition again? A tensor of order d has rank 1 if it's the outer product of d vectors, which we saw yesterday in the non-symmetric case. And in the symmetric case, a tensor has rank 1 if it's the outer product of the same vector with itself d times. And we might need to add a scalar lambda in case we have d even and we're working over the real numbers, for example. Okay? And a decomposition of the tensor t is just expressing it as a sum of rank 1 terms in the symmetric case, in the non-symmetric case, and in the symmetric case, we express it as a sum of symmetric rank 1 terms. And the smallest r for which such a decomposition exists is the rank of t in the ordinary non-symmetric case or the symmetric rank in the symmetric case. Okay, so I'll give you a quick application of tensor decompositions in mixture modeling. So I claim that tensors are joint distributions, or joint distributions of discrete variables are tensors. So suppose that we have d random variables, x1 up through xd, which are discrete. So let's say xi takes the values from 1 through ni. Then their joint distribution is an n1 by n2 up through nd tensor, t, whose entry at position I1, I2 up through id is the probability that x1 is I1, x2 is I2, up through xd is id. Okay? So what does it mean that these variables are independent, for example? Well, it turns out that independence is equivalent to the tensor, the joint distribution tensor being rank 1. So let's see why that's the case. So independence is equivalent to the probability that x1 is I1 up to xd is id factors as the probability that x1 is I1 times the probability that x2 is I2 up through the probability that xd is id. And if you write this in outer product form, it precisely means that the tensor t factors as the outer product of the marginal distributions of the xi's. So here, p of xi is a vector of length ni, and that's just the distribution of the variable xi. So it's a rank 1 tensor. Okay? And what happens if now there's a hidden variable z such that the variables x1 up to xd are independent given z equal to j. And here the hidden variable z will take r values. Well, this means that the conditional distribution of the x's, given that z equals to j, is a rank 1 tensor. It factorizes as these rank 1 conditional marginal distributions. And so the total joint distribution of the xi's can be written as the sum over all the values that z takes, so j from 1 to r, the probability that z is j times this conditional rank 1 tensor. Okay, and so basically if you observe data coming from these xi's and z is hidden, you might want to decompose this tensor. So when you observe data, you're going to get an empirical distribution, so it will be an empirical tensor, which will be close to this actual joint distribution tensor. And you might want to decompose it in order to find out this hidden information regarding the hidden variable. So one example could be the xi's are the words in a document, the first D words in a document, and maybe you observe a lot of, let's say, articles, and each one has a hidden topic, Z. And if you decompose the tensor, you will find the distribution of topics and also the distribution of words for each topic. That would be one example. Okay? All right, so tensor decompositions could be very useful. However, they turn out to be quite different from matrix decompositions. So on the plus side, most of the times decomposing a tensor into R rank 1 terms, where R is the rank, is usually unique. Whereas for matrices, the decomposition of a matrix is never unique unless R is 1. Because if you can write a matrix as A times B, then you can multiply in the middle with any invertible matrix C. So you can have A times C times C inverse B. And that will give you infinitely many possible decompositions for the matrix. On the other hand, finding the decomposition of a tensor is NP hard. Finding the rank is NP hard. Finding tensor eigenvectors, which I'll define in a little bit, is also NP hard. And those actually are the critical points to the rank 1 approximation problem for a tensor. And therefore, it's hard to find the best rank 1 approximation to a tensor. And what's more is that the set of tensors of rank at most R, when R is at least 2, is not closed. And therefore, if you have a tensor and you want to approximate it by a rank R tensor, well, that approximation might not even exist. So let me show you an example. So consider this sequence of rank 2 tensors. So for each k, we have one rank 2 tensor, like this. Here, E1 and E2 are the standard basis vectors, let's say in R2. It turns out that as k goes to infinity, it converges to a rank 3 tensor. And this is quite surprising, and it doesn't really happen for matrices, right? But it does happen for tensors. So yeah. So in order to alleviate these problems, people study structured tensor decompositions, where you can impose structure on the elements of the decomposition and maybe get better properties. So today I'll be talking about orthogonal tensor decomposition, and we'll see that such tensors can be decomposed efficiently via, for example, the tensor power method. There are also other ways to decompose them efficiently. All of their eigenvectors can be found efficiently. And moreover, the set of such tensors is closed and can be described via quadratic equations. Very, very nice quadratic equations. And it turns out that also small perturbations of such tensors can be decomposed, again, using the same power method. And time permitting, I'll tell you about incoherently decomposable tensors, or equiangular tight frame decomposable tensors. So here we try to extend the set of orthogonally decomposable tensors by replacing orthonormal bases with an equiangular tight frame, and see whether we can decompose those using the same methods. Okay, so before I get into such tensors, I want to tell you one fun fact about symmetric tensors and polynomials, and I'm sure a lot of you already know this. So an equivalent way of representing a symmetric tensor is of order d and dimension n, is by a homogeneous polynomial of degree d in n variables. So suppose that d equals to 2. If we have a matrix T, then the corresponding polynomial is a quadratic form, ft, and it's equal to x transpose tx, where x is a vector of variables x1 through xn. And if we expand this expression, we get exactly the sum over ij of tij xi xj. And we can, instead of, this polynomial encodes the same information as the tensor T. And similarly, and this is because T is symmetric. Similarly, for a general symmetric tensor of order D, it corresponds to a polynomial ft of x1 up to xn, which is given by, if you look at the sum, it's the sum over all of the indices I1 up through id from 1 to n of t I1, I2 up through id times xi1, xi2 up through xid. And if you think about it, in the matrix case, you take x transpose times t times x, so you're contracting t with x along both of its dimensions. And in the case of a d order tensor, you contract t with x along all d of its dimensions. So when d is 2, you get x transpose tx, but when d is larger, you do x transpose tx, and then you keep contracting along all of the dimensions. Okay? And a rank 1 tensor T corresponds to a polynomial ft, which is the power of a linear form. So if T is lambda v to the tensor power d, then ft is just lambda times this x dot v to the power d. And decomposing a tensor corresponds to decomposing the corresponding polynomial into sums of powers of linear forms. And we're going to see that this is just a very beautiful way of thinking about these, and it makes a lot of expressions easy to write down. Okay, so now let's get into orthogonal tensor decomposition. And I'm mainly going to focus on the symmetric case. So symmetric tensor T is orthogonally decomposable, or sometimes we call it ODECO, if it can be written as, if it can be decomposed as before, so sum over I, lambda I, vi to the tensor power d. But now we require that the vectors v1 up through vr be orthonormal. Okay? And so since there are at most n orthonormal vectors in Rn, that means that R is at most n. And therefore, the rank of such a tensor is at most n. And so what's interesting is that for a matrix, the generic rank is n. But for a tensor of order d, a symmetric tensor of order d, the generic rank is on the order of n to the d minus 1. So it's quite big. It's not just n. So therefore, these tensors have a very low rank. So they form a very small subset of the set of all tensors. So they're very, very, very special. We'll see they're very nice, but they're very, very special. Okay, and so here are some examples. So I claim that all symmetric matrices are orthogonally decomposable, because by the spectral theorem, we can write every matrix T as V transpose lambda V, where V is a matrix with rows an orthonormal basis of eigenvectors, and lambda is the diagonal matrix of eigenvalues. And if you write down this expression, if you factor this out, you see that it equals to the sum over I from 1 to n of lambda I vi transpose, or lambda I vi to the tensor power 2. Okay, so and since the vi's are orthonormal, then the matrix is orthogonally decomposable. So every matrix is orthogonally decomposable. And here's another example. You can form a diagonal tensor, so pick the vi's to be the standard basis vectors, and then take the sum of ei to the tensor power d. That's just a diagonal tensor with ones on the diagonal. Okay. So how do we decompose these tensors? I claim one way to decompose them is via something called the power method, tensor power method. And to tell you how to perform the power method, I first have to define eigenvectors of tensors. Okay, so what are eigenvectors of symmetric tensors? So suppose that now we have a matrix again, so d equals to 2. What is an eigenvector? Well, w is an eigenvector if tw equals to lambda w. So tw is parallel to w, and tw here is the sum. It's a vector whose ith entry is the sum over j, ti, j, wj. Okay, so similarly, we define an eigenvector for a tensor of order 3. So if t is a symmetric tensor of size n by n by n, then w is an eigenvector with eigenvalue lambda if tw squared, which is defined as the following. So tw here was contracting t with w along one of its dimensions. And then in the case of d equals to 3, we contract t with w along 2 of its dimensions, so along d minus 1 of the dimensions. And when we do this, we get a vector out. Okay, so we get a vector whose ith entry is the sum over jk of tijk, wj, wk. Okay, and this has to be parallel to w in order for w to be an eigenvector. And lambda is its corresponding eigenvalue. And so we can define this for a general symmetric tensor of order d. In this case, an eigenvector of t with an eigenvector with eigenvalue lambda is a vector w such that tw to the d minus 1, which is exactly contracting t with w along all but one dimension, is parallel to w. Okay, so it's defined like this. It looks complicated, but it's really just contracting t along all but one dimension. And in this case, two eigenvector-eigenvalue pairs, w lambda and w prime lambda prime, are equivalent if there exists a scalar t such that t to the d minus 2 lambda equals lambda prime, and tw equals w prime. So note that if d was 2 and we had matrices, then lambda would just be equal to lambda prime, right? But since we have tensors, then we have to scale the eigenvalue as well. And the reason I said that it's very nice to consider these as polynomials is that to define an eigenvector it's much simpler using the polynomial. So W is an eigenvector of T with corresponding eigenvalue lambda if the gradient of F at W equals to d lambda W. Okay, so it's a much nicer way to say this. And this actually gives us a way to describe the set of all eigenvectors of a tensor, because X is an eigenvector if the matrix whose columns, which has two columns, the first one the gradient of F at X, and the second one X, it has to have rank at most 1, and therefore all of its 2 by 2 minors have to be 0. So this gives rise to a set of polynomial equations which define the eigenvectors of T. And so here is an example. Let T be the diagonal tensor with a 3 by 3 by 3 diagonal tensor with 1s on the diagonal, and the corresponding polynomial will be x cubed plus y cubed plus z cubed. So when is x, y, z an eigenvector? Well, whenever the gradient is parallel to x, y, z, and the gradient is this one, 3x squared, 3y squared, 3z squared. And so if you take the 2 by 2 minors of this and divide by 3, you get these 3 nice equations. And we can easily solve them, and there are 7 solutions. So the first 3 are exactly E1, E2, and E3 back. And then next we have E1 plus E2, E1 plus E3, and E2 plus E3. And then finally we have the sum of all 3. Okay. Okay, and it turns out that if T is orthogonally decomposable with the decomposition sum over I, lambda I, vi to the tensor power d, then all of the vi's are eigenvectors of T, just like in the example we had E1, E2, and E3 are eigenvectors of T. And they also have corresponding eigenvalues, the lambda i's. So let's check this. So we can just contract T with vk to the power d minus 1 times. And we're going to get these dot products, which are all 0 unless I equals to k, and this is exactly equal to lambda k vk. So all of the vectors in the decomposition of an orthogonally decomposable tensor are eigenvectors. Okay? And this is quite rare for tensors. And so in the next few slides, we'll discuss whether there's a way of finding these vectors, because if we can find these vectors efficiently, then we'll be able to find the decomposition. Because if we find the VI's, that gives us the decomposition of T. And also, we'll see whether these are all of the eigenvectors of such a tensor. As we saw in the previous example, there were 7 eigenvectors, and only 3 of them were the ones in the decomposition. So we'll try to describe all of them. Okay, so it turns out that the vectors v1 up through vk are actually a special type of eigenvector called a robust eigenvector. So a unit vector u is called a robust eigenvector for a tensor T if there exists some epsilon such that whenever you start in a ball of radius epsilon around u, and you repeatedly iterate this map, this is called the tensor power iteration map. So you take a vector, and then you contract T with this vector along d minus 1 dimensions, and you normalize, and you keep doing this, then you always converge back to u. So anywhere in this ball you start around u, you converge back to u. And note that this is the fixed points of this map are precisely the eigenvectors. Okay? So, and it turns out that for an orthogonally decomposable tensor, the vectors vi in the decomposition are precisely the robust eigenvectors. And so the set of vectors which do not converge to some of these vectors under repeated iteration of this power iteration map has measure 0. So with probability 1, wherever you start in Rn, you're going to converge to one of these vectors. Okay? And so this gives rise to an algorithm for finding the decomposition, finding the vectors v1 up through vk, or vr. And it's really simple given the previous slide. So you start off with a tensor T, and then you repeatedly start at a random point in Rn, and then you iterate this map, and then you converge to one of the VI's. Then you can easily recover the corresponding lambda I by contracting the tensor with VI d times this time, not d minus 1. And then you can subtract this entry, lambda I VI to the tensor power d. So this is called deflation. And then you do this until your tensor is basically 0. And then you return the vectors that you found. So this gives you the decomposition of such a tensor. And let me just say that the tensor power method iteration can be written like this, but it's also very nicely expressed as just taking the gradient of f at theta and normalizing, if you prefer to do it in this language. Okay, and there's been a lot of work, a lot more work on this in the recent past, and people have shown that if you start in an almost orthogonally decomposable tensor, then you can use the same algorithm, and you can find the vectors vi up to the same error as how far you were to the original, to the orthogonally decomposable tensor. And also, there are other methods for decomposing such tensors. Okay, so there's an eigenvalue decomposition of the slices would give you that, and there are, today in my session with Tammy Kolda, we heard another method of doing so using Jacobi type algorithms. Okay, so, so let me tell you about all of the eigenvectors of an orthogonally decomposable tensor. Recall that they're just given by some equations, which are the 2x2 minors of this matrix, this n by 2 matrix. So it turns out that if a tensor T, symmetric tensor of order D, has finitely many eigenvectors, then their number is exactly d minus 1 to the n minus 1 divided by d minus 2. And so if d equals to 2, note that the numerator is divisible by d minus 2. So if d equals to 2, you can easily check that this exactly equals n. So this works for matrices as well. But it also works for general tensors of this size. And indeed, we can recover exactly this many eigenvectors of an orthogonally decomposable tensor. So let T be an orthogonally decomposable tensor of order D at least 3. And suppose that its decomposition is given exactly like this, so sum over lambda I vi to the tensor power D. Then T has precisely the expected number of eigenvectors, and we can give a formula for them. Okay, so, and the way it works is as follows. It looks kind of complicated, but it's actually not so complicated. So first we pick a number k, and then our eigenvector will be a linear combination of k of the vectors v1 through vn. Okay, so we pick k, and then sigma here says which k of these vi's you pick. So basically, you pick k vectors from our set of vi's, and then we take a linear combination, and this linear combination has some specified coefficients. So the coefficients depend on the lambda i's, and also we have to multiply by some d minus second roots of unity in order to get all of the possible eigenvectors. So this might look a little complicated, but so for example, if k equals to 1, then we just pick one of the vi's, and this just shows that each of the vi's is an eigenvector. Okay? So let's go back to the example we had before. So we have this diagonal tensor, then the eigenvectors are given as follows. So the eigenvectors are going to be linear combinations of several of the vectors ei. So if k equals to 1, we just take linear combinations of one of them, so that's all 3 of them. If k equals to 2, we take linear combinations of pairs, and it turns out that all of the coefficients, all of these lambda i's to the power negative 1 over d minus 2 are all 1 because the lambdas are 1. So in this case, we just get e1 plus e2, e1 plus e3, and e2 plus e3. And if k is 3, we get the sum of all 3. And the reason this is nice is that, as I said, for a general tensor, it's NP hard to find any eigenvector, whereas for these, we can find all of them, and we can write a formula for these eigenvectors. So it's a very nice story. Okay. All right. So far, I told you, I was talking about these orthogonally decomposable tensors via their parametric representation. So we express them as a sum over I of lambda I vi to a tensor power d. But can we find an implicit representation? So can we find equations that define the set of such tensors? Okay? And it turns out that the set of orthogonally decomposable tensors is defined by some very nice quadratic equations. Okay, so let me start by telling you what happens if you have a symmetric tensor of order 3, so an n by n by n symmetric tensor, and when it is orthogonally decomposable. This is a very surprisingly looking result. So given such a tensor, we can define the following product. So you take two vectors, x and y, in Rn, and you form this product star, which takes x and y and produces another vector, which is given by contracting x along with x along one dimension and with y along another dimension. Okay, so if T was a matrix, you would do x transpose Ty and you would get a number. But since T is an order 3 tensor, when you do this x transpose Ty, you get a vector back. So x star y is a vector. And it turns out that a symmetric tensor T is orthogonally decomposable if and only if this product star is associative. So x star y star z equals to x star y star z for every 3 vectors x, y, and z. And I claim that this actually gives rise to some quadratic equations in the entries of T that tell you when T is orthogonally decomposable. Because note that this product star, so when you take x and y, the resulting vector actually has entries that are linear in the entries of T. Okay? And when you do this product twice, then you get a vector whose entries are quadratic in the entries of T. And so 2 such vectors are equal, and therefore you get quadratic equations. Okay? And in general, if you have a tensor of order D, then we can see precisely what these quadratic equations are. So you start off with the tensor T, and then you multiply it with itself along one of its dimensions. So if T was a matrix, you would do T transpose T, or T transpose, doesn't really matter because it's symmetric. But if T has order D, when you do this multiplication, you end up with a tensor of order 2D minus 2, okay? Because there's D minus 1 dimensions left from one of the parts and D minus 1 dimensions left from the other part. And it turns out that T is orthogonally decomposable if and only if this contracted tensor is fully symmetric. Okay, so it's, to begin with, it's symmetric if you perturb any of the first D minus 1 indices or any of the last D minus 1 indices. But it's orthogonally decomposable if and only if you can switch, you can permute any of the indices. Okay, and I just have a quick example. First of all, every symmetric matrix is orthogonally decomposable because when you do this product, you get exactly T transpose T, and that's always symmetric for any matrix. So that proves one more time that all matrices are orthogonally decomposable. And again, if you have an order 3 tensor, then you can write out these equations, and they look like this. Okay, so they're just quadratic equations in the entries of the tensor. Okay, so I want to say just a couple of words about non-symmetric orthogonal tensor decomposition. So recall that just a non-symmetric decomposition is writing a non-symmetric tensor. You know, it has size n1 by n2 up to nd as a sum of rank 1 terms. And if you want to make it orthogonally decomposable, then you have to require that in each of the terms, the vectors ai are orthonormal, and the vectors bi are orthonormal, and the vectors ci are orthonormal among each other, and so on. So let me give you an example. So I claim that all matrices are orthogonally decomposable. So if we take an n1 by n2 matrix, you can find its singular value decomposition and write it as U sigma V transpose. And U and V are orthogonal matrices. And if you factor this out, you get that the matrix is precisely equal to the sum over I of sigma I ui vi transpose, or ui tensor vi. So every matrix is orthogonally decomposable because the ui's and the vi's are the columns of U and V, and U and V are orthogonal matrices. And another example, again, is, for example, a diagonal tensor. Like before, that one is also orthogonally decomposable. And I'm not going to say much about this, but these can also be decomposed efficiently, and we can find their singular vector tuples. So for a non-symmetric matrix, you don't have an eigenvectors, we have singular vector pairs. And for a non-symmetric tensor, we have singular vector tuples. And again, we can find all of these and write the similar, slightly more complicated looking formulas for them as well. And just one thing I wanted to mention is there's this common conjecture that says that if you have a symmetric tensor of rank R, so remember I defined rank and symmetric rank. So if you're given a symmetric tensor, you can find its usual rank decomposition without requiring the entries here to be symmetric. So this could be the usual non-symmetric decomposition. The conjecture is that if it has rank R, then it also has symmetric rank R. Okay? So one direction is clear. If it has symmetric rank R, then clearly it also has rank R, but the other direction is not clear. And there's been a lot of development. There's actually a counterexample to this conjecture by Shitov. And it's been proven in certain cases. For example, for 4 by 4 by 4, n by n by n tensors of given rank by Anna Siegel. And there's a lot more work, a lot more work proving it for different families of tensors. And I just wanted to say that orthogonally decomposable tensors are very nice because for them we can show that the Common conjecture is true. Okay, so they're also very special in that the conjecture is true. Okay, so if you have a symmetric tensor and it has an orthogonal decomposition in the non-symmetric sense, then there is one also in the symmetric sense. Okay, and I would like to end with telling you about how one might extend the set of such tensors. So as I said, a general tensor of order D, a symmetric tensor of order D, has rank 1 over n times n plus d minus 1 choose d. So this is on the order of n to the d minus 1. It's quite big. And an orthogonally decomposable tensor has rank at most n. Okay, so this is a very small subset of the set of all tensors. And how can we enlarge the set of orthogonally decomposable tensors but try to pertain some of their nice properties? And one thing that we've tried doing is instead of looking at orthonormal bases, we can try to look at tight frames. Or I will tell you about, in particular, about equiangular tight frames. So a set of vectors v1 up through vr is an equiangular tight frame. If, first of all, when you take the matrix with columns, the vi's, then v transpose is r over n times the identity. And the vi's have unit 1, so this is called a unit norm tight frame. And then if there exists a constant such that all of the dot products of the vi's are all equal to that constant in absolute value, then it's called an equiangular tight frame because all of the angles between different vectors are equal. And if the constant c is 0, then we have an orthonormal basis. Okay, but if the constant c is something else, then we have a different set of vectors, which could be, the number of such vectors could be more than n. And we say that a tensor is equiangular tight frame decomposable if it can be written, if it can be decomposed like as usual, but now the vi's form an equiangular tight frame. And some examples of these, for example, in R2, it's the Mercedes-Benz frame, like the logo. And in R3, we can form some 4 vectors in R3, and they have equal angles. And I wanted to tell you about this little result. So if we take this special tensor, if we take the Mercedes-Benz frame, or any rotation of it, and we form this tensor T, then it turns out that V1, V2, and V3 are precisely the robust eigenvectors of T. Okay, so the vectors in the decomposition are exactly the robust eigenvectors, and they can be recovered by the tensor power method. And we believe this is true for general equiangular tight frames that have n plus 1 vectors in Rn. And so this really means that all of their dot products are actually negative 1 over n. So it's a very special family of equiangular tight frames. And it turns out that we have these are the robust eigenvectors. And I want to end with some pictures of the tensor power method. So, so we have let's say we have the Mercedes-Benz frame, and we have this tensor from here, from this theorem. And here the blue region shows all of the points such that if you start there, you converge to this vector. The green region shows all the points such that if you start there, you converge to this one, and similar for the red. And this is the tensor power method dynamics for this tensor. And if D is even, so these 6, 8, 10, and 12, and all of the even numbers, the regions of attraction are very nice. They're exactly these little triangles here. But if D is odd, so we have 5, 7, 9, and so on, we see this interesting fractal behavior. So these are still robust eigenvectors because there is a ball around them such that you always converge there, but in the space in between is just a fractal looking space. Okay, and so I'm interested in other structures and algorithms that would allow for a fast decomposition, just like the one I talked about. And what would happen, for example, if we took a tensor network, if you know what this is, and maybe imposed some structure on the tensors that are at the vertices of the tensor network, if you know what this is. I think maybe that's one way of going about it. I don't know. That's it. Thank you.
Are there any questions?
Let's do some pause.
Oh, there we go. Oh.
No, take it.
I think people are watching it. So.
Okay, is in the mixed model interpretation, is there any interpretation there of ODECO or ETF conditions?
Right, great. So I actually, because I knew this would be a short lecture, I removed this slide. So thank you for the question. So basically, in the mixture model question, the decomposition, all of the vectors there are non-negative. So this is not possibly, it can't be orthogonally decomposable. But there is, so you can do something called whitening. Basically, in this mixture model, you would observe, let's say, the joint distribution of the first 3 words and the first 2 words, or the first 3 vectors and the first 3 variables and the first 2 variables. That will give you a matrix and a tensor that have the same decomposition, except for the tensor power is 1 is 3 and 1 is 2. And this allows you to do something called whitening, which will make the order 3 tensor orthogonally decomposable. So it's a very nice procedure that allows you to do that. So you can use the composition of such tensors in precisely this mixture model case. There's a very nice paper by Anand Kumar et al. Where they do this.
Thank you.
Other questions?
Is there a Hermitian side of this story? It seems to be interesting that it's for the real numbers are so particular.
Yeah, so we proved together with Jan and Ada and Neil that so you can do this for unitarily decomposable tensors, and we find similar equations. So, but in this case, they're quartic equations, and also for alternating tensors as well.
One more?
Okay, so are there similar results for ETFs in complex spaces? In CN, for example?
So we can find equations that define the set of such tensors, but I don't know if there are results about actually decomposing them. Yes. I don't know if that was, I think that was your question.
All right, question down here.
So maybe a follow-up to see
Yeah. Oh.
Yeah, so actually half of my question was going to be related to what Ramona's asked, which is going back to these ETFs.
Okay.
Well, I guess 2 questions. One is, you have this conjecture that real simplices are always going to give you this decomposition. What do you see as kind of the bottleneck in the proof from moving from the Mercedes-Benz frame to a higher dimension?
I think it's just more indices.
Okay.
Yeah, I think we're very close to proof, and all of the experiments show that it's true. So I think it'd be actually interesting to look at even other ETFs as well, and I can talk to you about it later.
Yeah.
Where the elements in the decomposition will be eigenvectors of the tensor, just like in this case. And I think these simplices are not the only ones.
Mm-hmm.
I think you can construct other ones as well.
Yeah. Maybe we'll talk more about.
Yes.
Yeah.
Very good. Any other questions? Okay, reminder, there's a quick advertisement after we thank Elina Robeva one more time.
Yeah, thank you, John. So I would like to advertise another prize and present a call for nomination for the Stephen Smale Prize. So here are the main details. So the Stephen Smale Prize, the goal is to recognize major achievements in the interface between computer science, pure mathematics, numerical analysis, and applied mathematics. And the topics covered by this conference is a subset of the topics that are considered for the Smale Prize. The Smale Prize will be awarded next year at the Conference of the Foundations of Computational Mathematics in Vancouver. So this is also an advertisement of that conference. The eligibility for that prize is a little broader than for the Early Career Prize for SciAm. So while this prize is set for really quite shortly after PhD, for the Smale Prize, it's mid-career, so it's more or less 10 years after the PhD. The exact rules are in the website. If you can think of somebody that you think would be eligible, please prepare a nomination that consists of a brief letter, the CV of the nominee, and 3 letters of recommendation. And the deadline is coming up. It's September 15th, and Michael Singer, who couldn't come here, is the secretary of FOCM, and he collects the nomination. And here is the website of the Smale Prize. That's Stephen Smale. And you can see that the previous 3 winners are part of this community. So this is really a big intersection with the nominees, with the winners. And the winner will get what's called a gumböt. So while here for the Smale Prize, John was responsible. This has some Hungarian connection, so that's the prize. So please consider your most talented young colleagues for this prize. Thank you.
Thank you all. Just a reminder, please come back on Friday for the business meeting. The actual prize. What would you like?
We need at least one picture with you giving the prize.
Okay, we need a picture.